Okay, so we're right here at 11 o'clock now, so we'll go ahead and begin. First off, good morning. I'm Joel Neidig. I'm the Director of Research and Development at ITAMCO and your host for today's America Makes TRX webinar series. So a little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes Membership Director, Tiffany Westbay, directly. A few important notes before we kick off the series. At the end of the presentation will be an opportunity for brief questions and answers for the Q&A. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we'll ask those questions during the Q&A. We'll do our best to get to all the questions and get them all answered, and if not, we'll be able to follow up with further questions via email at the end. So today's webinar is the mitigation of thermal distortion in metal additive manufacturing through thermo-mechanical simulation. That is a mouthful. Our presenter today is Dr. Hao Ping. He's the Vice President of Product Development for Atlas 3D. And I'm just going to give you guys a little bio on Dr. Hao Ping. Dr. Hao Ping received his PhD from the University of Missouri, Columbia, in mechanical and aerospace engineering in 2014. He was a Missouri Honors Award awardee. And Dr. Hao Ping is very sophisticated with modeling of complex structures and materials, as well as fluid flow, phase change, and heat transfer and laser material interaction. Things that he's developed, finite element codes for solid mechanics and heat transfer problems, multi-scale and multi-physical modeling of metallic additive manufacturing, design and model of acoustic metamaterials for vibration suppression and wave absorption, and structure and material behavior under extreme conditions such as crack propagation, penetration, collision, and phase change. So all I can say is that Dr. Hao Ping is extremely smart. So without further ado, I want to pass it over to Dr. Hao Ping, and he'll get into the presentation today.
Thanks, Joe. Hello, everyone. Today I will talk about mitigation of thermal distortion in the additive manufacturing process with the thermo-mechanical simulation of the whole process. So first of all, what is additive manufacturing? So AM, or additive manufacturing, generally refers to the method which you create 3 objects or parts in a layer-by-layer fashion. So with the AM method, people can create 3D objects directly from the CAD model. So why we use AM? Compared to the traditional subtractive manufacturing method, what's the advantage of the AM? This is a figure. We can see that with AM, we can build the part very fast. We can build very complex parts, and we will consume less energy and less material. There are many different kinds of metal additive manufacturing process in the market. So based on the process, they can categorize into 4 different types: the material extrusion process, direct energy deposition process, sheet lamination process, powder bed film process. And almost all those methods, they can print metal parts. And there are quite a few. They are very popular in the market, like the FDM, fused deposition modeling, the lens system, laser engineering, lens shape, and also the SLS, selective laser sintering, and the DMLS, direct metal laser sintering process. So in our presentation today, I will focus on 2 different types of process. One is the direct energy deposition process, and the other one is the powder bed film process. So direct energy deposition process, or DED, it usually uses metal powders or metal wire as the feedstock, and usually it uses a laser beam as the feed source. And feedback control is usually required in this type of machine because we need to make sure the nozzle is always perpendicular to the part surface and make sure the nozzle keep a constant distance away from the part surface. On right side shows you the lens DED machine. You can say that we use the feedback sensors to do the feedback control. There are several different advantages of the DED system. First thing is that it can build very large parts. It can build parts up to several feet long, and it's very flexible in using materials. You can, for example, you can mix different type of metal powders, and you can build composite and heterogeneous materials. And you can even change the metal powders or metal wires during the build process. The other popular metal AM process is called direct metal laser sintering process, or DMLS. Usually, metal powder is used as the feedstock, and people use laser or electron beam as a heat source. If you use laser, the part is usually built in inert gas environment. If you use electron beam, usually you need to build a part in vacuum. This video here shows you how to use the DMLS to build a rocket motor throat. There are many advantages of this method. First is you can build extremely complex parts with this method, and you can also use different materials, including titanium, aluminum, stainless steel, and lots of others. And the disadvantage is that the process is relatively slow. To build a part, it usually takes hours or even a few days, and you can build only relatively small parts with this method. There are lots of different applications for metal AM, including automotive, biomedical, and aerospace areas. You can also design new structures and materials with the metal AM method. Here, what I show you is that people use the metal AM method to build a structure with negative coefficient of thermal expression. And we can also build new materials, or people even call it functionally graded material with the DED method. You can see that we can control the concentration of some gradient manually so that we can achieve the material properties. However, there are also lots of changes in the metal AM process. Because in all the metal AM process, we need to use either laser beam or electron beam to melt the metal feedstock, and the thermal gradient and the cooling rate in metal AM process is usually very large. And this will induce lots of thermal stresses in the part. And the thermal stresses usually will cause the crack. And in a global view, the thermal stress will cause the distortion, thermal distortion of the part, and making your part out of specification. And also the other problem is the delamination, both delamination in the part and the delamination of the support structure from the build platform. The delamination is a very serious problem in the powder bed fusion process. You can see that when you build a part, if you have a delamination of the support structure from the build platform, you will have very large part distortion even during the build process. And when your recoater blade is trying to spread a new layer of metal powder, it will collide with the distorted part, and this will stop the build process, and you need to start everything from the beginning. So in order to solve those problems, we need to understand what's the physics behind the metal AM process. The physics can be very, very complex, and there's no simple analysis. This figure shows you we use the electron beam to melt the metal powder bed, and you can see that tons of physics happening there, including heat transfer, conduction, radiation, convection, and also fluid flow, phase change, melting, solidification, and laser absorption, and there are lots of things you need to consider, such as the capillary force, wetting, dewetting. You can see that the physics is very complex, and the heat transfer you see here is that when we melt the laser beam, when we melt the metal powders with the laser beam, heat will conduct from the melt tool region to the other part of the part. And the heat also will transfer to the chamber through convection and also through radiation. And we found that convection and radiation are small in comparison to the conduction. This is especially true for metal. And the conduction into the powder bed is also small because the conductivity of the metal powders is about only 2% of the bulk conductivity. So actually, most of heat just conducts through the part and support during the AM build process. From the thermo-mechanical point of view, the whole build process can be divided into 4 steps. So in step 1, the laser beam will melt the metal powder into a melt pool. In the second step, the melt pool starts to cool down by stirring liquid phase. In the third step, the melt pool is fully solidified, and the further temperature drop will cause lots of thermal stresses in that region. And step 1, step 2, step 3 will keep iterating during the layer-by-layer build process. And I call step 3 the thermal contraction, where this is where the stress is accumulated. And after we build the part, usually we need to cut the part of the substrate. And in this step, I call step 4, you will see lots of distortion of the part, and I call it stress relaxation. So the question here is that, can we model the complex physics in the metal AM process? To answer this question, we need to answer the other 3 questions. So what are the important physics that you worry about? And what are the partial equations, the Gaussian equations you need to solve? And what's the relevant length scale and time scale you care about? The other question is that, can modeling help to solve the thermal stress problem? We know that the poor build settings, like the scaling speed of the laser or laser power, or improper control of the heat transfer, can lead to lots of thermal stress and can make the part out of specification. If we can model the whole build process, if we can simulate the physics, it helps us to understand what's the physics that lead to the build failure, and it will help to determine what the conditions that will impact the build failure. And finally, if we can optimize the build process, all the parameters, build orientation, support structure, it will help us to preclude the build failures. So, for example, there are quite different types of binding mechanism used by metal AM, and the most popular one is the floor melting. In the floor melting, we can build a floor density part. That's why people like it. However, in real build process, when we have different laser power and different scanning speed, we will get different profile of the part. For example, if your scanning speed is too fast or the laser power is too low, you will get partial melting. And if you have a very high laser power or very low scanning speed, you will have this boiling effect. In order to achieve this continuous high aspect ratio profile, you really want to have a good combination of the laser power and scanning speed. So in order to model the whole AM process, the first thing you need to think about is how to model the laser metal interaction. So we know that lasers have a spectrum. So when we model the laser metal interaction, we need to model how the material absorbs the laser. We can see that for different wavelengths of the laser, the absorption of a single material is different. For example, here, if you want to melt the copper with a laser beam, you don't want to use the CO2 laser because with the CO2 laser, the absorption rate for copper is pretty low. Most of the energy just reflected. The state-of-art modeling method for the heat source is called the ray tracing method. The idea is very simple. So you model a single beam of laser with multiple rays, and you will track how each ray is reflected within the material. And every time you have a reflection, you need to calculate the absorptivity both in perpendicular and parallel direction to the plane of incidence. So in this way, if you calculate all the absorptivity of the rays, you will get a good idea how much energy is absorbed by the material. The other method of modeling the heat source is the continuum model. So in the horizontal direction, we can model the intensity profile as a Gaussian density function. And along the vertical direction, usually people use empirical model, or sometimes they just model the energy of exponential decay. And finally, we can model the heat source as Q dot here. You can see that the PV is the beam power, and the eta E is the energy absorption coefficient. The Gamma equations are not new. They just basic principles. For example, the conservation of mass, conservation of momentum, conservation of energy. And if you want to model the free surface flow, you need to model the surface tension, and you want to use the Young-Laplace equation. And if you want to model the heat, the stress in the solid part, you need the force balance equation here for solid. If you want to solve the free surface flow, usually people will use this called a volume of fluid method. The idea is that you decompose the whole simulation domain into scales, and with each scale there's a variable epsilon associated with it. So if epsilon is 0, that means the scale is filled by air. There's no metal material here. If epsilon is 1, that means the scale is filled by metal. But if the epsilon is in between 0 and 1, that means that scale, the interface between the air and the metal material. So in what approaches can we take to model the AM process? We can model the whole process with different details. For example, when we model each layer, we can model the real layer, which is about 40 or 30 microns thick. And we also can model a thick layer. I call it super layer here. So each super layer represents multiple real layers. And when we model the laser beam, we can apply the heat to the whole layer at one time, or we can divide the scanning surface into patches and apply heat source one patch by one patch. Or in more detail, we can model the real scanning path of the laser beam. For the support structure, we can model the support of continuum body with effective physical properties, or we can model the real lattice structure of the support. Here, what I show you is the high-fidelity modeling conducted by Lawrence Livermore National Lab. You can see that they model each single metal powder, and they model how the laser beam scans through the metal powder and how the metal powders are melted. And you can see the dynamics of the fluid flow. You can see the surface tension effect. So this model includes almost all physics happening in the AM process, and it compares very well to the experimental observation. The problem is that in order to do this high-fidelity modeling, it takes takes lots of hours, even you use supercomputer, and the simulation domain is very small. So we need to really rethink how we can model the whole process. This figure shows the AM model with different time scale and different length scale. If it's impossible, it's computationally intensive to capture the physics as all the length scale and time scale. So we really want to think about what time scale you want to simulate and what length scale you want to simulate. And for optimization, for real application, we need to simulate parts with size up to 1 millimeter. So how to simplify the simulation so that we can make our model more efficient? We know that the heat transfer is described by this partial differential equation. The left side is the stored energy, and the middle side is the heat transfer through conduction. And last part is the energy from the laser. This partial, if you want to solve this equation with a finite element, it takes long if you model the AM process. And we know that the thermal system and electrical system have some similarities. So a good idea is that we model the heat transfer in the same way we model the electric current, so that we can simplify the 4D PDE of the heat transfer into a network of thermal resistance and capacitance. And we did that, and we can model the heat transfer when we build this part both horizontally and vertically. You can see that when we build the part horizontally, the thermal gradient is larger because the cross-sectional area is larger and the heat transfer is faster. And when we build the part vertically, we need support structure over these overhanging features. I didn't show it here, but we include that in our simulation. And you can see that how heat transfer from the overhanging area because it's hotter. The good thing about the TCN or thermal circuit network is that it's very efficient in comparison to finite element. We modeled the same process with finite element and takes 10 hours and 30 hours for the horizontal part and the vertical part. But for the TCN, it takes only 1 minute and 12 minutes, much efficient. So how about the thermo-mechanical process? How can we simplify this process and make these processes more efficient? So the idea is that first we break the part into elements, and then we use finite elements to model the stress balance for each element. The second idea is that although the build process, in the build process, the temperature profile is transient, is changing all the time. But actually, the stress accumulation is very slow. So you can solve the problem with the quasi-static method. So you only need to look at temperature points in a few temperature points in the build process. So here, what I show you is the distortion from the other 3D software and the comparison to the experiment. This experimental result is from Lawrence Livermore National Lab. You can see that when we build this triangle horizontally and vertically, we will have different distortion. And the prediction from our software compared to the experimental results pretty well. So let's come to talk about optimization. So what parameters can we optimize? The first thing we come to our mind is the laser power and the scanning speed. Usually, for most of engineers, we just use the default value of laser power and scanning speed in the machine, and we don't need to change it very often. The other two parameters we need to change every for every build is that the build orientation and support structure. So every time we build a part, we need to ask ourselves, what orientation we need to use? Do we need to build this part vertically or build it horizontally? Or what type of support structures we can use? There are many types of support structures, and different support structure will affect the heat transfer and will also affect the thermo-mechanical process. This is the general optimization method. So because you need to deal with different geometries of the part, so usually we will take the CAD file as the model input, and we will initialize the part with one orientation, and we will set the support structure for this orientation, and we will predict temperature history and predict thermal distortion. If the thermal distortion is minimized, we can see that, okay, the optimization is done. Otherwise, we need to change the orientation and do another iteration of optimization. So the question is, the hard part is here, how can we check the thermal distortion is minimized? So we need an optimization engine to do that. So we use this method called the direct method as the optimization engine. The idea is very simple. You can see that the largest rectangle here is the search domain. So every time in each iteration of the optimization, you subdivide the whole large rectangle into smaller rectangles, and you will find the rectangles which may contain the optimal value, and then you need to subdivide those rectangles. Those rectangles are highlighted by yellow here, and this method is invented by Daniel Finkel. You can refer to the direct optimization algorithm user guide if you want to know more information about it. One thing to mention is that this optimization engine can search the optimal value both globally and locally. So with the direct optimization algorithm and a very efficient metal AM simulation tool, we can optimize the build orientation and also support structures in this way. So every time you set an orientation, you send to the model and evaluate the objectives. You can set different objectives. You can set distortion of your objective, or maximum stress in the part, or strain energy in the part. So in this way, you will achieve the optimal objectives with the direct optimization engine. So here, what I show you are a few case studies. In our with our L3 software, we evaluate more than 100 different orientations, and we search what's the best orientation, give you the minimum thermal distortion. And finally, we find the orientation shown in the picture here, and we also build a part in this orientation. We measure the distortion of the part with our coordinate measuring machine, and we compare the distortion to a part built horizontally. You can see that when we build a part horizontally, we will see very large distortion, about 447 microns. And if we build the part with the angle, we will get only 100 micron the distortion. So the reduction of thermal distortion is about 76%. We also study a more complex part, which is the orthopedic handle. You can see that, again, we evaluate about more than 100 orientations. So we do thermo-mechanical analysis for these different orientations, and we find the orientation which minimizes the thermal distortion. And finally, we will build a part with the angle, and we also measure the part, both the part in optimal orientation and the part built horizontally. You can see that there are almost no distortion when we build a part with the optimal orientation. So here what I show you is the viewer in the About 3D software, and this part is optimized for minimum build time, and we can show you what's the thermal distortion there. You are free to go to this portal About3D.xyz, and you can create a username and password and have a try. And if you need a free coupon to test the software, just email us. Thank you so much. And I would like to take any questions you have.
Great, thanks, Hal. So the first question we have is, so how, let's say I don't have a metal printer yet, okay? I'm just coming on, this is my first, it's first time in the metal, getting into metal additive, direct metal laser sintering, powder bed fusion, whatever you want to call it.
Yeah.
How do I, where do I, is this a software that I need, is this a software that I can use, right off the bat? I mean, is this something that is something I should look at getting into?
Yeah, sure. So this About 3D software basically is used to model the layer-by-layer build process. You can model different materials. What you need to do is to add the material properties into the when you try to simulate the part. We have a place you can input your material properties. You can just customize your material properties there, and you can simulate the plastic material.
Great. Okay, here's a question. At a company, they're doing R&D with high-power fiber array lasers, 7 to 19 beams. We are scaling the power, beam spot, and shape size and scan real-time by using optical sensors to monitor the melt pool. Okay, so this is more of a keen question if they're interested in these efforts. Let's see what this one is. So in many cases, optimization of process parameters are limited due to required material properties or surface quality. Thus, what about optimization, shape, or topology? Support structures in terms of cost and quality.
So we can, as I talked about, there are lots of parameters we can optimize. The laser scanning speed, the laser power, or the build orientation, and the support structure. Yeah, most of the time people don't want to change the shape of their STL design. If they want a new design of the original part, sure, I think topology optimization is a very good way to go.
And as far as the cost and quality, how is there a feature inside this software that can tell, I'm like, hey, I'm optimizing, is there a feature in there that will tell me the cost? And
yes, there's a feature allow you to estimate the cost of the build process.
Great. Okay, here's a great one. What kind of computer hardware is required to run these simulations?
This is a good question. So actually, our software About3D is running on the cloud. So we are using Amazon Web Service. So you just need to go to the website and simulate the simulation. You don't need to run the software locally on your own computer.
Great. How is the contact with the other powder addressed in terms of thermal modeling? How is it the contact of the part to the powder?
How is the contact with the other powder addressed?
I'm wondering if the part. I'm wondering if they're asking about the part contact with the. I think you kind of modeled. I don't know if you modeled that in the. You kind of went over that model in the previous slides.
I think if you are asking about the contact between the recoater blade and the part during process, no, we are not modeling that. We just model each layer is added in the build process. We are not modeling the real, physical contact between the recoater blade and the part. We are not doing that.
The surrounding non-sintered powder.
Yeah, he followed up there. He said heat transfer wise.
Oh, heat transfer wise. And great. Okay. Yeah. So how long did this simulation take? How?
This is a good question. So we are evaluating hundreds of different orientations. So actually, we need to simulate the whole build process for hundreds of times. So we must make sure each time is very efficient. So for each single orientation, it takes about, it depends on the part size. For normal size of, I'm talking about, for example, 100 millimeter size, the heat transfer takes about a few minutes, and the thermo-mechanical model takes about 30 minutes.
Great, and I believe this recording will be made available. Let's see, how can we get credits to evaluate this tool? Is there a
sales?
Yeah, you can go to you can just Google Atlas 3D, or go to you can go to our website, and you can contact our customer service.
Great. Yeah, sales at atlas3d.xyz, I think.
Yeah, thank you.
Email addresses. And I know there is actually a coupon code available to the America Makes membership, I believe, until December 15th. So there's a couple more days in activation on that code that was emailed out to membership. Is it possible to predict the location of crack initiation with the software?
So right now we are modeling the part. So we are building a macro model. So we are not modeling the microstructures and the crack formation. We are not doing that.
Okay. And I believe we're trying to just look through the previous. Trying to look at see if there's any other questions on the Q&A. And I'm just scrolling through here. Great. I don't think we have any further questions from the current audience. So I'd just like to thank everyone again for being on the America Makes TRX webinar series for today. Once again, if you have further questions, you can reach out to the presenter contact information, which is info at atlas3d.xyz. You can also reach out to sales at atlas3d.xyz as well. There will be a post-webinar survey going out to all those who participated. So we really do appreciate those that take the time to provide the feedback to America Makes to continue to improve and strengthen our additive community. And a reminder that if you think you or organization would be interested in sharing the TRX webinar series, please fill out the form that follows the presentation or reach out to Tiffany Westbay. Thank you all for attending, and have a happy holiday. Thank you.